Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the sequel lecture, lecture number 24 of the SwayamPrabha course titled Marine Renewable Energy Systems, Analysis, Design and Development, offered jointly by me and Dr. Basanagoda Patil. This course is offered under the auspices of SwayamPrabha portal by the Department of Maritime Engineering at IIT Gandhinagar. So friends, welcome to the 24th lecture where I am discussing further on the wind energy harvest systems as a sequel lecture number 2. In the previous lecture of this sequel, we discussed about the supporting systems which can host a wind energy farm offshore. So our focus was to talk about floating offshore wind turbines. So we picked up an example problem of an offshore wind turbine supported by spar platform And equivalently, we developed another model where the same wind turbine is supported on a triceratop, which is one of the novel systems designed and developed for exploring oil and gas in ultra deep waters. So, the idea is to take these wind turbine locations far away from the coast at a water depth close to about 2400 meters. You will notice, friends, this platform, which is part supported wind turbine, taken as example reference, is installed at 1000-meter water depth. So, as you go away from the coast and deeper waters, you get very high wind velocity. So, the efficiency of generating wave power or wind power can be much higher as you go to ultra deep waters. Of course, system design also becomes equally complicated. Let us understand the system design perspectives first before we move on to discuss the complications. Let us say I am talking about a spar platform and a triceratop. More details of the dynamic response behavior of these two platforms can be seen in a parallel SwayamPrabha course titled Maritime Structures offered by Department of Maritime Engineering at IIT Gandhinagar. But for information's sake, in this specific lecture, let me give you some brief overview of this behavior. Spar is a cylindrical buoy anchored to the seabed using mooring lines. It is a deep draft buoy, means that if this is my water level, about 80% of the cylinder is in water. So, this supports a hull, where the hull supports a mast which has got a rotor which has got a fan. So, this is my wind turbine. Whereas triceratop is supported on 3 buoyant legs. It has got a hull. The hull again has the mast supported, the mast has a rotor and it's got a fan. So, this is the wind turbine. But the distinct feature is the buoyant leg and the hull are connected using ball joints. And further, this buoyant leg is connected to the seabed using pre-tensioned cables. And the water level is approximately here. This is my mean sea level, this is our water depth. This is the mean sea level, this is water depth. So, spar are generally commissioned at a water depth of about 1000 meters. Triceratops are commissioned about water depth of 2.4 kilometers. Okay. It has got a single cylinder which is deep drafted. This has got multiple buoyant legs. Now, the beauty about this particular platform behavior is what we are focusing. One, when the platform legs are subjected to rotation, like pitch and roll, they will not be transferred to the hull. How? Because the ball joints will restrain this transfer. Whereas when the legs are subjected to heave motion, this will be transformed to the hull. So, in the heave degree of freedom, the system remains monolithic. In the rotational degrees of freedom, the system is partially isolated. Okay. So, that is the difference between the behavior of this system compared to this. Let us see whether this gives me any advantage in holding the wind turbine. So, we have got two systems now on the screen. Both of them are geometrically modeled in ANSYS space claim. Both are 5 megawatt wind turbine. The specification of the wind turbine are given in NERL website. We have taken the designs and the data from there, which I showed you in the previous slide. So, now the mast from the level is about 100 meters, which is similar here as well. The system is supporting on buoyant legs, where the buoyant legs are isolated from the deck by ball joints. Let me mark it here in red color. And furthermore, these legs are connected to the seabed using mooring lines, whereas these are connected to the seabed using teethers. So, we have both of them readily available in the geometric model in ANSYS space claim, which now for discussion. The numerical model is generated in ANSYS workbench. I will show you the video of both of them at the end of this lecture. So, you could see that enlarged view of the spar supported wind turbine, where the mooring lines are connecting the spar at different locations circumferentially and connecting them to the seabed. The power cables pass through, which are the umbilical cables which are used to transfer the power later. A 5 megawatt wind turbine is connected to the hull, and this specific connection is what we see here. Okay, this is about the numerical model very briefly of spar supported wind turbine. Let us go to the triceratops supported wind turbine. So, you will see the buoyant legs are supported by pre-tensioned axial cables, which we call teethers, to the seabed. The depth is much higher compared to the spar. The depth is much higher compared to the spar. You can see that here. And it has got a triangular hull, whereas spar had a cylindrical hull. It has got a triangular hull, more space is available. The mast is made to rest comfortably on the hull, which is 80 meters side, a big space, and is resting the turbine. The turbine superstructure is similar what we support on spar as well, and the power cable goes through, and the pre-tensioned axial cables are called as tendons or teethers, and these are called buoyant leg structures. So, BLS stands for buoyant leg structures. The model was simulated and helped by me. So, credits are also due to Dr. Yogesh who helped me in conducting the research study in parallel. So now let us see the responses. Let us first start with the wind velocity time history. The wind velocity time history has got three components. Let's say along x we say u, along y and along z, three components. So let us say u component along x, v component along y, w along z, let us say. You notice that for unidirectional wind, the x-axis component is shifted from the mean, okay, whereas the other two components are acting at the mean level itself. So, the x-axis component acting along the surge direction creates a drift to the system, okay. Then from that shifted mean position, it oscillates. So, that is the time history considered for wind velocity. If you look at the average, let us say the V and W component is about 5 meter per second, whereas the x component is about 10 meter per second, that is varying from 5 to 15, so 10 meter per second. So, the wind velocity or 12 meter per second, the wind velocity is much higher in the x axis compared to these two, and the history is taken for about 300 seconds applied to this wind turbine superstructure. Let us look at the forces generated, the time history which this wind is generating. The force along the x-axis rises as high as about 1100 kilonewtons, whereas along y and along z, let us talk about y, the value along sway direction is not much, whereas it generates force in the heave direction, okay, which is about 2500, that is force in z axis. So, what we are concerned about, the rotation for the force acting along x, the rotation about y, which is pitch, which phenomenally high. So, my is much higher, is about 50,000 kilonewton meter, whereas the roll and yaw, this is roll, this is yaw, okay, this is mz, so yaw, mx, so roll, my pitch. So, the pitch is very high, is about 50,000 kilonewton meter compared to the rotation about roll and yaw. You will notice that the end moment created by the wind force at the supporting system of the mast is fairly high compared to that about x and y axis. So, this is where the design becomes very challenging. It drifts in x axis, you will notice that here. It also causes huge surge in x axis, whereas in sway it is lesser, but in heave it is more. So, the force is acted along x and z axis, which are phenomenally high. In addition, there is a rotation about y axis, which is pitch. So, now I am activating the design for three major forces along x, along z, about y. Out of these three, these two are translational, this is rotational. This causes axial forces, this causes moment at the base, for which the mast and the TLP or the triceratop should be designed for. This is the force history which is taken for the full 300 seconds, you will notice that the force history is active for a value about the maximum value touching about. If you look at the mean value of the force, then the net effect is reduced, but there is a overall shift of the moment which is happening from the 0 value. Okay? Because of symmetry of the system, the rotation about z, the yaw moment is very less, it is only 100. Because the wind approach angle can be not exactly 0 degrees to the tower, can also cause roll. Therefore, there is some value of roll present in the system initially, but later it is more or less minimum, but the pitch is very active and surge and heave on the axial forces active in x and z directions respectively. Now, let us look at, I am sorry for the spell check, this should be John Swab. Friends, this should be John Swab spectrum. So, this is a spectral ordinate being used for the design. So, at 0 degree, you will notice that the wave spectrum which is being used for the floater for the Triceratop reaches the spectral ordinate very high. As the wave direction spreads out, it goes practically 0. Okay, got a very good wave force also acting on the system compared to the wind. Now, I have got a system which is having wind plus wave. Okay, both of them are typical and critical for the design. Let us see the hydrostatic results of both spar and Triceratop. Spar has got a displacement of 15,000 cubic meters, whereas all the legs together amounts to similar. Okay. The water plane area of spar is about 176 square meter, whereas all the legs together amounts more or less same. The shift from center of gravity to center of buoyancy measured from buoyancy to gravity. Gravity is down, okay, so minus. You will notice that spar has got 16 meters shift from COG to center of buoyancy, whereas buoyant legs are more. It means by design, Triceratops exercise more stability compared to spar, which can be seen as a metacentric height. The metacentric height is higher in Triceratop buoyant legs compared to that of spar. Therefore, one can say by design, Triceratop floater can be more stable compared to spar. Okay. The restoring moments which are seen in spar is about, let us say, I can write it here, is about 42.6 meganewton meter, whereas in the buoyant legs this is only about 21 meganewton meter. One can ask a question, how there is a reduction in the restoring moments offered by the legs? This is because partially the restoration is also offered by the ball joints present between the deck and the buoyant legs. Now, let us look at the motion responses in all 6 degrees of freedom for spar and Triceratop. You will notice that spar shows very high surge compared to Triceratop. Spar shows similar heave compared to Triceratop. Spar shows very large moment in pitch compared to Triceratop. So, Triceratop shows much lesser moment, similar heave, lesser surge compared to spar supported wind turbine. Friends, is a great advantage. This is a great advantage. So, Triceratop supported floating offshore wind turbine shows lesser surge, lesser pitch moment and equivalent heave. It means this is stable, because heave is a stiff degree of freedom. Lesser moment and lesser displacement makes the design more safe. This is about the motion response. Let us move on to the natural period of spar supported wind turbine and Triceratop supported wind turbine. In surge, sway and yaw, which are flexible degrees of freedom, spar shows about 123 seconds, whereas in surge, sway and yaw, Triceratop shows about 800 seconds. So, the natural periods in flexible degrees of freedom are fairly high compared to them, which make the system more flexible, at the same time more stable. More flexible because periods in soft degrees are larger, more stable because in heave degree the periods are same. Similar to pitch and roll. So, in rotational degrees of freedom, the periods are similar. In heave degree of freedom, which is the vertical stiffness, the periods are similar, which ensures stability. In flexible degrees of freedom, periods are much larger, making the system flexible, which enables the ball joint to get activated to absorb this. Similarly, friends, since the periods in surge, sway and yaw are higher, it offers more damping to arrest this. So, about 25% damping is offered by the system, which is also coming from the ball joints, whereas spar does not offer this damping in these degrees of freedom. That is, in surge, sway and yaw is about 1.5%, whereas in Triceratop it offers about 25%, which comes major contribution from the ball joints. Whereas in heave degree of freedom, the system offers damping of 2.3% in spar, whereas here it is lesser because it is hydrodynamically damped because of the buoyant legs. So, the environmental damping applied to the system comes as a participating factor to improve stability of the system. So, no compromise on stiff degree, where the periods are most similar. Active degrees on flexible systems make the Triceratop more responsive and flexible compared to this. Since they are very flexible, more damping is offered in these degrees of freedom. So, that is the comparison between the natural periods and damping ratios of a spar supported wind turbine and Triceratop supported wind turbine. Let us see the responses. Look at the surge response, which is very flexible in in Triceratop. So, because of the ball joint, though it is flexible, but the response is very minimum, friends, compared to spar. Though the system is flexible in surge, the response is very minimum. However, when you talk about roll response, spar exercises more compared to triceratops. Let us look at the sway response is more or less similar. Talk about the moment, the pitch response. Spar exhibits much more, whereas triceratops exhibits very minimum, friends. It is because of the ball joint. So, it is safe in moment degree of freedom. Let us talk about the heave response. Triceratops exhibits more heave response, exercising participation from the buoyant legs. So, the buoyant legs equally participate in exercising the heave response, whereas in yaw, Triceratops is practically 0. So, in all active degrees of freedom, you will notice that Triceratops supported offshore wind turbine shows positive responses encouragingly compared to the tough spar. Let us look at the mooring lines. Spar supported mooring lines showed a maximum value of about 4,900 kilonewton, whereas Triceratops supported mooring lines showed only a maximum of 1/4 of this. It is only 1/4 of this, friends. So, mooring line tension is also not much. Therefore, there is no fatigue failure initiated in Triceratops supported wind turbines. So, therefore, friends, let us come to the summary of this lecture. The hydrostatic results of the spar buoy supported wind turbine are comparable with that of Triceratops supported wind turbine and conform to the preliminary design. Higher metacentric height of Triceratops wind turbine offers better initial stability against overturning. Ball joints placed between the legs and the deck restrain rotational responses. Therefore, it is an added advantage for the design. Triceratops supported wind turbines offer 50% higher restoring moments compared to displaced volume. A reduction of 50% maximum surge and sway responses in Triceratops supported wind turbine confirms its adaptability for deep waters. Roll and pitch responses in Triceratops supported wind turbine are only 15% compared to the tough spar buoy. So, it is an improved performance indicator for the design. Triceratops supported wind turbine shows significant reduction in cable tension as well. The proof of concept is established, and friends, more importantly, as such, wind turbine support in ultra deep waters is a very scarce application in the literature. It is not yet attempted in research front. So, the presented study is a very interesting overview for you to learn and innovate new offshore wind turbine systems at ultra deep waters, which is very interesting and quite advantageous. More results can be seen in the specific published paper of Journal of Institution of Engineers, published, authored by me, Yogesh, Giorgio Serino, Sangvi and Aishwari Gohil. So, the full detail of the paper is available in this DOI. So, you can please go through this paper for more understanding of the results, and this has got select references which are available on the screen. So, friends, thank you very much for listening to this lecture, and you would have understood that offshore wind turbine systems are also feasibly acceptable systems which equally can help us harness wind energy in offshore wind farms. Floating offshore wind turbines are good alternates, and in that aspect, Triceratops supported wind turbines showed many advantages compared to the previous existing spar supported systems. One can also look for horizontal axis wind turbine and vertical axis wind turbines in offshore systems. Hope this lecture would have been intuitively interesting for you to follow. Please stay connected for further more lectures on this course. Thank you very much. Namaste.